This podcast is supported by Siemens, your partner for industrial-grade AI.
So, hello everybody and welcome to a new episode of our Industrial AI podcast. My name is Robert Weber and my guest today is Cees Snoek from the Netherlands. He is a professor for computer science and he has several roles at once. Research at the University of Amsterdam, research at Atlas Lab and at the Qualcomm Lab, and one of the most important representatives on the topic of deep vision. Welcome, Cees. It's an honor to speak to you. Good morning.
Hello, good morning, Robert. My pleasure to be here this morning.
Is everything right, or did I miss something?
No, it's more than sufficient. Yes, thank you.
Let's first talk about the labs I mentioned, the Atlas Lab and the Qualcomm Lab. What is the Atlas Lab and what is the Qualcomm Lab? What are you doing there?
So the Atlas Lab is our collaboration with TomTom. TomTom is in the business of map making, and with the Atlas Lab, we are trying to enable what we call high definition maps. So the goal is so TomTom drives around in the world with cars collecting data of how the environment looks like, and the goal is to transform these recordings into high definition maps that they can use for their business.
Okay, so it's a navigation business, isn't it?
It's the navigation business, but also giving insights in traffic beyond navigation of the car, so to say. So to create these high definition map, new research is needed in computer vision, in 3D computer vision and 2D computer vision, to sort of like transfer these the recordings that these cars make while driving around, and to transfer these into these high definition maps. And this comes with RGB camera data, but also with LiDAR data, with point clouds, and to make sense of this, so to say.
So the goal is for autonomous driving?
That's one of the goals, yes. So these high definition maps are very useful for autonomous driving. So autonomous cars would need these maps to reach their autonomy, so to say.
Which role does AI play in this mapping?
Well, so the AI is sort of like the tool to make sense of the data. So to give you an example, how to combine camera data with LiDAR point data, and how can you infer that an object is indeed a car, or that it is occluded, or that you can sense the environment and identify all the objects of interest that the autonomous car at some point need to be aware of, so to say.
And what is the approach are you guys taking?
In these labs, these are very fundamental research. So what we're trying to do, we are not making the product, right? That is not our goal. So the goal of the lab is to innovate and to come up with new AI tools, so to say. So think about new object detectors, new semantic segmentation, new 3D point cloud interpreters, these kind of things. So that also in these labs it's very important to do knowledge transfer. So we transfer the knowledge of the PhD students to the engineers, to the scientific engineers inside the company, in this case, inside of TomTom. Because they get this new knowledge, they also sort of like start to think, hey, wait a minute, for our own business, this could be a useful tool, or if we adapt it a little bit, we can bend it and sort of like help reach our own deliverables. So one thing is the PhD students do fundamental research. The research can be protected in patents, so that's also a benefit for the industry partner, in this case TomTom, but also the knowledge exchange, so that the people inside of TomTom also get the new knowledge and exploit it for the business case, so to say.
So what means deep research? Do you have an example what you are doing there?
Deep research or deep vision?
We can switch to deep vision. If you use their deep vision, then we can go there, yeah.
Well, deep vision was the name we gave to one of our other collaborations, which was the QVA Lab with Qualcomm, mobile chip company. And there the idea was mostly because we joined two research groups from the University of Amsterdam, one focusing on machine learning and deep learning, and one traditionally more focused on computer vision. And we essentially took a keyword from both. So the deep learning and the computer vision became deep vision. Well, the funny thing is that nowadays, when we started, it was not yet the case. But nowadays, of course, computer vision without deep learning is very hard to imagine, or in any case, hard to get published. So for vision now, everything is deep. But in the lab, we do more than, we also do deep learning for general purpose domains. So we also consider typical machine learning topics like optimization, spiking neural networks, federated learning, differential privacy, these kind of things, without a vision component per se.
So this is in the Qualcomm lab, right?
Yeah, this is in the Qualcomm lab, correct.
Let's switch to this deep vision is your main field of research. When we have the postcard, we see a lot of vision applications in the industry. We could talk about it every week, I think, about computer vision solutions. So what is the difference you are working on?
We do pretty much what other people do in the field as well. So lately we have been very interested in transformers. I'm sure you have been discussing transformers in one of your podcasts before. So transformers are interesting in the sense that they have been originally designed for machine translation, so a natural language processing application. And what people have been doing is use those transformers as is, so as defined for language, and apply them to vision problems. And my biggest surprise is that this sort of works out of the box. So without changing or adapting it to the peculiarities of the vision modality, you can sort of like run a tool designed for language on a vision problem. Now, of course, vision is different from language. It already starts with the tokens, right? In language, you have the characters or the words in a sentence that you can tokenize, but in vision, this is quite different. And there are all kinds of problems that are unique to vision that you don't have in language, like multi-scale, locality, and translation invariance. So what we're trying to do now is to sort of like equip transformers with inductive biases that come with the vision modality, so that they are no longer so much dependent on huge amounts of data and compute, so as to say, to make them more efficient.
And how do you do that?
So one thing we know is, I mean, computer vision has been revolutionized by deep learning, but there have been many good ideas before deep learning in computer vision too, right? And there are many inductive biases that people have studied that are very relevant also in these modern days. So one of the things is, for example, in if you dive into the depth of the transformer and you start to see how does this attention mechanism, this self-attention mechanism work, you will see that in vision it doesn't make sense to treat each token as an individual word. So what I mean to say is that what people are doing, they vectorize image features in exactly the same way as language tokens, without taking the local connectivity of these tokens into account. Right? So if you zoom in to a picture, you will see that neighboring pixels have a relationship. They are often very similar, and there cannot be huge changes in a local area in an image. And by throwing this fact of nature, so to say, by throwing it away, you can compensate for it using huge amounts of data. And that is what the first vision transformers at least did. They demonstrated, look, be competitive with convolutional neural networks, sort of the default in vision, if we throw enough scale at it. So if we throw enough data and we show it enough examples, then it will find these regularities from the data. Our point has been, well, that's great. We don't have the scale in the compute that our friends at Google and Meta have. So we have to be more clever with the resources we have. But what about if we inject these inductive biases from the start? Then you need less data, and you will it will also result in faster learning, so faster convergence of the algorithms. So this is what we have done in one of our recent papers, actually, for object detection in 2D and 3D.
Do you see there a use case for this technology for industrial applications, or is it only research?
Our focus is only research, of course. I mean, this is an object detection tool that we have sort of like improved with this boxed attention, as we call it. And this is a general purpose tool that has been used by many, and in many applications. Many applications start with detecting what are the objects in the image.
When you spoke about the language topic, and we see a lot of big language models, do you see there's an option to develop big vision models, or it doesn't make sense?
Oh, no, definitely. That is already happening. Yeah, we live in interesting times, because I think it's for the first time that, or at least in the long time that I can remember, that vision gets a lot of inspiration from natural language processing.
Is it a surprise for you?
Yes and no. No, in the sense that language processing has a much longer history. So it's in that sense a more developed community, you could say. Yes, in the sense that it was not typically the area where innovations that were very relevant for vision came from. And that has changed.
So the innovation came from the hardware, right?
Yeah, vision also got a lot of inspiration from machine learning traditionally.
Okay, but the technical invention always focused on hardware, the best camera, and getting better.
Sure. That was also an important driver. So the hardware enabled sort of like the innovation. But now sort of like we're scanning the NLP community to get ideas for vision. And one of the big developments in NLP is these huge language models, GPT-3, BERT, and what have we, all these combinations. And what we are seeing now is that also these foundational models that combine vision and language are becoming a big thing. You might have heard of Clip from OpenAI. There's another model called Line and Flamingo. So there are lots of models are being proposed, and these models are really, really powerful. Maybe you have heard about DALL-E 2. Based on a text prompt, it can generate an image. I think earlier this week, Facebook released a tool, text to video, if I recall correctly.
Yes, I saw it on the social networks. Yeah,
and this is sort of like the first tool that generates a very short video clip from a text snippet. So it's called Make a Video.
Now we're talking about the big models. You mentioned DALL-E or Clip. We had an episode with the guys from Monolith AI. It's a little bit like DALL-E for engineers, what they are doing. I don't know if you know them. They are from UK. But we have these big models, and these big models are produced by companies. You mentioned Facebook, Google, whatever, OpenAI. What is your position as researchers? What is your next step? What are your focus? I think 20, 30 years ago, it was your task to build these big models. And now the private companies are building these big models. What is the research perspective on big models? What are your tasks to do in the next years?
Yeah, this is a very good question. And to be honest, I struggle a bit.
Mm-hmm. That's good for me.
With the question, in the sense that these huge foundational models require a huge amount of data and huge amount of compute. And we have quite some compute at the University of Amsterdam, so I can do my research. I do a lot of research on video, so that also takes compute. But I cannot use all my resources to replicate a model like Clip. I simply cannot afford it, and I also don't think I want it. Right, so that I would occupy my cluster for a few months to use all the GPUs to replicate a model of OpenAI. So, as an individual researcher with the group, I don't see a reason to compete along these lines. On the other hand, these models are big resources, and we use them for our research. I also don't want to be dependent on models that are provided by industry, from which I don't really know what is the internals of the model. So yeah, should I invest in huge compute and try to build my own models anyway? Should I unite the entire country of the Netherlands to say we're going to build Dutch foundational models?
Dutch vision model?
Yeah, that could be. Or do I unite Europe or join an effort that tries to unite Europe and to build European foundational models from people in academia? That could be. So I haven't figured it out yet.
But I think it's a problem for research because private companies are doing research, and what is the research for the universities?
Maybe we can find flaws in these models or identify why they are not trustworthy, and maybe come up with ways to improve these models along certain dimensions, or to hint at where are they brittle, where do they fail, where can they generalize over unseen domains.
I think that this is the topic explainable AI for research, but I think, in my opinion, researchers don't want to explain something for another; they want to invent something. Huh?
Well, there are also researchers who want to explain, but I am probably more in the other camp myself, because I can also be satisfied with an algorithm that is not explainable. I mean, if I design an algorithm that tells me that I have a certain disease, much more certain than my doctor, I would go for the algorithm, right? Even if I cannot explain how it got to its decision. Having said that, replicating these big foundational models is not really doable for a university professor. So then you have to ask either new questions, join forces, or debug them and hint at fatal flaws.
Let's talk about a little bit about the future of vision. What kind of application, what kind of technology you are looking for the next 5 years when we talk about computer vision?
5 years is a really long time span.
2 years.
I mean, things change so fast in vision these days that it's really hard to look ahead for 5 years.
So let's take 2 years.
So a few problems I identify. So one is that in vision, still the common practice is to train and test on data sets which have sort of a similar distribution. So that means what the algorithm sees at test time is quite similar to what it has seen during training. For example, I train my self-driving car on images from Germany, right? So from all over Germany, it has seen all the surroundings there. And now I'm going to test it in Namibia, in Africa. Now, I can tell you it will fail on the first encounter of a rock or an object it has never seen in Germany. So how can we attack distribution shift problem?
With artificial data?
Is a possibility. So this is a real problem of deep learning networks because it learns, at the end, it learns correlations in the data. So it has difficulty handling correlations it has never encountered. Now, how can you make sure that unseen correlations are still processed in the right way? Well, one way is to use more data. More data, you can say, if you're Google or Meta, you just collect more data. An alternative is to use synthetic data. So that is a promising way, but it's not really, I have not seen it really working at scale. I think it still needs more research.
What is the problem, do you think?
Yeah, it's artificial. So it is, I think the realism of the artificial data is too far off still from what we see in the real world. But progress in creating artificial data with like these DALI 2 and diffusion-based models is going really quickly. So I can imagine that generating data soon will be a very effective tool for deep learning. The other way is to adapt the algorithm to prepare it for things it has never seen. So that can also be done. So this is a typical work in domain adaptation and domain generalization. Recently, a new line of work that I like a lot is called test time adaptation. That you use the image, in this case, for example, that you encounter at test time, and you start to do some inference on it. Of course, you cannot retrain on the image, but you can still get useful information from the image that allows you to adapt your model in such a way that it is better prepared to classify the unseen image.
How do you do that?
For example, by using a self-supervised loss on your test image, and in that way you can sort of like update your original model in such a way that without using any labeling or interaction, just by looking at the data and inferring the structure in the data, you can use it to adapt your model. And there are other tools you can use there too.
Do you focus on this technology?
Yes. Well, we find domain generalization and using also test time information in general an interesting approach. So we have been doing research on this dimension. The other topic that I think that remains of interest is what can we learn not from many data, but from little data, right? So we have been doing a lot in few shot learning. So that I think remains important.
So the few shot learning is connected to the guys from language processing because they also do that.
Yeah, everybody's doing that. For sure. So, but you can do few shot learning if you have a big foundational model. But I would like to do it without big foundational model because
how you want to do that then?
Yeah. Because else, I mean, that's easy, right? The big foundational model has seen so many examples already. Then with few shot, that's simple. But what can you do without? So that is a topic of interest.
But how you want to do it without a big model?
So we're looking into meta learning approaches. So learning to learn, so that you have solved a classification task in this couple of times, different classification task, and then you start to sort of like infer meta knowledge. What is the meta knowledge for this classification task? So if I have then a new classification task with a few examples, I know because I've seen so many classification tasks before that I can also solve this classification task, although it is a slightly different one than the ones I've encountered. Also, the role of memory is interesting here.
Sure, but the memory is not very big.
The memory is no, it cannot be very big because else you're back to foundational models. So in a way, you could say, how can we constrain all the dimensions of foundational models, and what can we then still get out of it, so to say. Another topic of interest, self-supervised learning, so learning without any labels, so you exploiting simply the structure in the data. Very interesting problem. The other one is causality, going away from learning correlations. Causality solves can also attack the domain generalization problem. That is an interesting. We are still investigating transformers. So that is also of interest.
I
And
think that's very interesting what you mentioned, I think 10 minutes before with the transformers. That's very interesting, I think, also for the industry.
yeah, definitely. And especially for maybe not for the big industry players, maybe for the medium-sized and smaller-sized companies who also want to do something with AI and don't want to be dependent on Google and Meta, right? So want to do it themselves. So that is of course a big market for AI. Oh, and fairness and trustworthiness of algorithms in general. That is a big topic.
You mentioned new algorithms, I think 10 or 3 minutes ago, to establish new algorithms. What about robust algorithms? What is it a research field in Amsterdam in your group?
Oh, definitely. No, yeah, robustness. So one of the dimensions of robustness is to this generalization across domains, right? So when the shift of the test samples, the distribution shift does not resemble the training examples anymore. So that is all about robustness, and also learning with a few labeled examples is also about robustness. So robustness is definitely a big topic, and not only in my lab but also in many other labs in Amsterdam, actually.
Finally, I would love to learn why there's so much going on in Amsterdam, because we had an episode with Sepp Hochreiter and he told us you have to interview the guys from Amsterdam because there's so much going on in Amsterdam right now in terms of AI. Why is Amsterdam the role model for Europe when it comes to AI?
Oh, yeah, that's a big question. Well, I've been thinking about this myself. I think there are several reasons. I think the first one is that we have two universities in Amsterdam, and both of them have bachelor and master AI program, and they have this already since the 90s.
Since the 90s, okay.
Since the 90s. I believe that in Europe, Edinburgh was the first university to have a bachelor and master program on artificial intelligence. And both the University of Amsterdam and the Free University Amsterdam followed soon after. So we have been doing AI for quite a long time. I think that is reason number one. And then reason number two is that we have also been doing public-private partnerships in the Amsterdam region, also already for a very long time. So we were used to working with industrial partners.
And I think the Netherlands are investing a lot per capita in AI, I think.
No, that is not true. That is not true. We are lag behind in Europe. We are the idiot of Europe in that sense.
Everybody tells me that. Zepp told me that in Austria, in Netherlands, it's the same, huh?
Yeah. No, the government has no. We are the only country in Europe without a serious AI program.
Okay.
So nothing is invested in AI research by the government. It's really poor.
Okay. I thought Netherlands is a role model by investing in AI.
No, so maybe that is the reason why we have been focusing so strongly on public-private for a long time in Amsterdam, because that is where we get most of our funding. So one more thing. I think what was also important for AI in Amsterdam was that Max Welling came back from US to Amsterdam to strengthen the machine learning research, at least in the University of Amsterdam. And then essentially then the deep learning revolution started, and we had all the ingredients in place because our research was heavy on database machine learning, so to say. Not necessarily neural networks. That was not really a big topic of focus in Amsterdam, but we were doing machine learning based on data in NLP, in information retrieval, in computer vision. So we were essentially perfectly prepared for deep learning. So when deep learning happened, so to say,
Was born, yeah.
well, yeah, or was revitalized. It was born already several times, and we were ready for it. I think that was sort of like the what happened. We were all these individual disciplines that had their own way of doing things, all adopted deep learning, and collectively that made us very very competitive and interesting. And because of our history of public-private partnerships, And our big talent pool, it was also natural to talk with all these big companies. And then what happened was that in 2014, Qualcomm was one of the first big tech companies to come to Amsterdam. They acquired a startup company, a small startup company that I was also involved with, Uvision, doing visual recognition and also on mobile phones. And Qualcomm established Qualcomm Amsterdam, and they noticed that the startup had a close connection with the university. They want to maintain that also for their office. And then the Cuva lab was born, so to say.
I did my research and I thought that the city of Amsterdam is also pushing the AI topic for the population with algorithm registry and more. How do you get these politicians to do that?
Yeah, this is a more recent development. Well, you have to realize that besides the two universities in Amsterdam, we also have a University of Applied Sciences, which is, of course, also very much into AI. So they have a big responsible AI team. We have two academic hospitals in Amsterdam that have recently merged into one even bigger one. And they have been doing a lot of medical imaging and artificial intelligence for that. And we have a National Cancer Institute also in the municipality. So we have a lot of knowledge institutes that are very deep into artificial intelligence research. Then Amsterdam has many tech companies. So Qualcomm has an office, Google has an office, Microsoft,
Bosch is there, Microsoft.
Bosch is there, but also Booking, TomTom, Elsevier, Adyen. Adyen, I'm not sure whether you know, but it's a big financial platform. So they are huge. So this is huge in the service industry using AI. And what we also have is, besides, we do not only have deep technical depth, but also anchoring this into broad societal breadth. So really sort of like making the AI applicable in society and also thinking about it.
I think that's important, yeah.
That's very important. And we have this cross in Amsterdam. And because the universities are not technical universities, these are broad universities. So we have all the sciences on board. So we have a very strong humanities, political sciences, and so on. And these are all also very interested in AI, and they provide the fresh perspective. Like, hey, yeah, you can also sort of like, you can imagine this algorithm. That's great, but what if we're going to apply this in society at large? What does that mean? Right. So we have this discussion going on, and I think that is what makes it very attractive. And also, the municipality has now recognized, hey, AI is here to stay. This is a big team, and Amsterdam can play an important role on the topic in Europe.
Keith, it was a pleasure to talk to you. Thanks for your time and greetings to the Netherlands.
Thank you so much, and have a great day.